Well, hello everyone. My name is Riemen van Rosen. I'm a researcher at Centrum Wiskunde en Informatica in Amsterdam, and I'm presenting to you live from Amsterdam. That's about approximately 12 hours difference from where you are. My talk today is about, or tonight, is about Cascade, a meta language for change, cause, and effect. I'm very happy to participate in the workshop on live programming, by the way. It's a great workshop. Let's get started. So, to tell you a little bit about the background and motivation of this work, I will tell you about a language I've studied called machinations. Machinations is a domain-specific language for game economies. Originally developed as a conceptual game design aid, machinations expresses internal economies, kind of like a marble machine that sits inside a computer game. And game designers develop the chutes and levers that players can use to make the marbles go in a specific direction. So that, for instance, if you get gold, you can get a quick reward, or you can invest it and then later on receive a bigger reward, but at a bigger risk. Now, I studied live game design. So what I wanted to do was to make a programming language out of machinations and to modify a game's mechanics while it is running for prototyping, playtesting, and fine-tuning gameplay. Over the years, I built many tools for machinations, let's say for formal analysis, for pattern-based editing, for live programming, and together with indie game developers, we did many case studies. And many of these tools could be characterized as mixed initiative, co-creative game design tools. Now, a common problem that I kept encountering while making these tools was that there is a general lack of enabling technology for these tools, in particular for the live programming part. And the objective is to develop language parametric enabling technology that powers live programming. Now, my approach is to develop Cascade, a meta language for creating these languages with interface and feedback mechanisms that drive the live programming. And to explain that a little bit better, I will talk about a coding cycle. So programming starts out with intentions, then programmers perform actions via some kind of user interface mechanism they interact with. That has effects inside a computer system, which then displays these effects some way, and then the programmer can interpret that and evaluate if they have achieved their intentions. And of course, live programming is all about speeding up these coding cycles. Now, where we sit in this talk is at the bottom of this cycle, namely, we're talking about effects mainly. So let's talk about the challenges I have addressed. So it's about prototyping live languages, and mainly about obtaining a REPL, a mechanism for coding, user interaction, and live feedback, so a read, eval, print loop. Secondly, it's about modeling languages, or modeling languages. So expressing the abstract syntax and the runtime state using meta models. Third, designing the side effects of these languages is difficult. So we need ways to express coding actions that work on the abstract syntax and user actions that affect the runtime state. And finally, the reason that Cascade even exists is that there is a need for accounting for runtime eventualities. And these express cascading changes in runtime scenarios, for instance, runtime state migrations. And that may sound a bit like a mouthful, but I will explain each point using a demo. And here it is. I programmed it for this talk using Cascade, and it's a very simple example called LiveSML. It's being used for other papers as well, just as in this paper. It expresses state machine languages, and it allows simultaneously programming and running programs. So in this simple scenario, a programmer creates a state machine doors. There it is. Then the programmer adds state opened and closed. So we're creating a little DSL here, a DSL program on the left. And by performing these coding actions, the program is being formed. So we see the program is slowly taking shape. And finally, we add the last transition for also being able to open the door. Now, the user can create a running state machine. It starts in the initial state opened with a count of 1, with a little star. And then finally, the user closes this door, and we see that the transition is made to a closed door. Well, so far, so good. Nothing too spectacular yet. Let's move on. Now, we have a running program already, but the programmer now adds a locked state. And this has an effect, namely TinyLiveSML adds a locked state to the running program as well. Now, the programmer creates another transition, lock, so that you can lock a closed door. And now the user can lock the door. So it's triggered and we see it transitions to the locked state. Yeah, so we saw that we can modify a running program. Now, finally, to show that migrations are necessary, the programmer is going to delete the locked state. And that has a lot of effects, namely TinyLiveSML removes the locked state from all running program instances. And it migrates the current state of our running state machine to opened to, as you can see, it also increases the count. Now, what's different from prior implementations of LiveSML is that TinyLiveSML counts only 213 lines of code in Cascade. And I will show you a little bit how that works. So the Cascade framework consists of 2 parts. And actually, we're now answering the question on how to prototype live languages. That's one of those 4 points that we saw before. So the Cascade compiler, it reads Cascade specifications and it outputs C#. And it generates language prototypes that integrate with a virtual machine called Delta. And the platform itself is implemented in Rascal. That's a meta-programming language and language workbench that I myself use. It's developed at the group that I work, and many other researchers use it as well. It's also used in education. Now, the generated language prototypes from the Cascade compiler contain several components. A generator, yes, it generates a generator that generates, when it's integrated with the Delta runtime, it generates transactions, changes over the runtime state and the abstract syntax. In addition, it has pre and post migrators. These are not components normally part of interpreters or compilers, but for this type of live programming, we need them because we need to migrate events that happen before and after every other event. And finally, it has an inverter because everything that happens can also be undone. Now, as a second part of the framework, there is the runtime, and it contains a REPL language, and that enables to perform user interactions and coding actions in a low-level way. And Delta is an extensible engine built in C# that interprets events and enforces change. It has several reusable parts, namely a scheduler that schedules actions as events, a patcher that commits transactions to the history, and a dispatcher that relays events to the right language, so that the scheduler can call the generator from the right language. It can call its pre and post migrators in order to achieve the right scenario based on the Cascade specification. So the next part, to model languages, expressing the abstract syntax and runtime state. This is actually relatively simple. It's well known. that you can use meta models. And here we see a class diagram of the TinyLiveSML abstract syntax with a machine, a state, and a transition, and basically not that exciting. The runtime meta model, on the other hand, is a little bit more interesting. You can see that it uses the abstract syntax. It points to that model using definitions. And a machine instance has a current state instance, and the state instance keeps account. Now, this is necessary in order for every machine to have its own runtime state. How to write this down? Well, in a simple notation that resembles object-oriented languages, so that you can model these class diagrams, these meta models in Cascade. The next part, designing side effects. So how to express coding actions that work on abstract syntax and user actions that work on the runtime state. Well, remember, the programmer created the doors, machine doors, and Delta interprets the effect of create. Well, here we see what that looks like in Cascade. You can program an effect, and this is not a method. This is actually more of a transformation, and its parameter promises that after this effect is complete, there will be a machine object in the future. Each of the operations inside the body of create are edit operations. And these are actually reversible operations that modify objects over time. Now, in Cascade, we also have bidirectionality, not only on the operation level, but also on the transaction level or on the transformation level. So every effect has an inverse with the exact opposite effect. So for every create, we also have a delete that does the opposite. However, you can also have side effects. And in these side effects, you can schedule what happens before and after every effect. So in the case of deleting a machine, it also deletes all of its states and all of the machine instances, because none of them would have a reason to exist anymore. Now, finally, the reason for the existence of Cascade is to account for runtime eventualities, to express cascading changes in runtime scenarios, such as runtime state migrations. So when the programmer deleted the locked state, TinyLiveSML removed and deleted the state from all program instances, and it reinitialized all instances, which results into the migration of our specific doors instance, but it might not do for other ones. And it gave it a new current state. And here in this snippet of code, we see that that is a result from remove state. So when you delete a state, it also removes it. And when it removes it, it has as a pre-side effect that it does this tidying up bit. And this is all traced so that when Delta executes it, you get a cause and effect chain that actually explains how and why everything happened. Now, the objective of this work is to develop language parametric enabling technology that powers live programming. The contribution is Cascade, a meta language for creating such languages with interface and feedback mechanisms for live programming. The challenges addressed, I've talked to you about and explained it a little bit, that it is about prototyping live languages with REPLs, modeling abstract syntax and runtime state, and designing side effects. Also, these side effects determine not only how it happens, but when they are executed, they can be transmitted back to the user, back to the programmer, and explain why it happened in terms of history. And it accounts for runtime eventualities. Now, current and future work is validating Cascade on 3 more complex languages, machinations that I introduced a little bit, behavior trees, and the questionnaire language. Each of these languages contain so-called fixed point computations that require you to check if a trickle effect is already complete. And since Cascade enables you to schedule events in the future, that also allows you to check if you are done. And so this is preliminary work, of course. Here I've just presented TinyLiveSML, and this more elaborate work is part of future work. And aside from that, well, I've shown you a little demo that had a handcrafted web UI on top of the REPL. What I want to do is to actually generate more intricate, more elaborate visual interfaces based on specifications, and to develop more interesting prototypes from there, so that this purple part of the circle that you see is also included in Cascade. Finally, Cascade is available online, and my slides there, a pre-recording of the talk and paper, everything is there. Yeah, that concludes my talk. Thank you.
Thanks, Remer. Okay, we have time for questions. If not, I have a question, Remer. So the types of the code that you wrote for Cascade reminds me a little bit of working with React, where components can like mount and unmount, and then they handle their own side effects and such. Sorry if I am not if I'm not knowledgeable about the history of this sort of like modeling or programming, but could you tell me a little bit about whether that approach, like how this approach extends to more complex programs?
So you're asking how an approach like Cascade will make more complex programming languages?
Okay, maybe I'll phrase it like, in the limit, if Cascade was really successful, how would it benefit your particular work and what you do?
Well, basically, it would be the language backend of all kinds of visual domain-specific languages for live programming. That is its ultimate goal. And for the machinations, I can express machinations in a few hundred lines of code. And previously, it was a huge amount of C++ code that was difficult to understand and hard to maintain. Basically, these type of languages couldn't exist because there wasn't any way to build them. And a similar effect can be seen with a live questionnaire language developed by Thijs van der Storm. The first versions of this language were a bit hard to understand. And now that Cascade is there, all these effects and side effects can be neatly expressed using abstractions that are suited for it. And yeah, the tradition of this work, I would say bidirectional model transformations. I think that work was big around maybe 2011. And at a certain point, it kind of stopped. And there were some languages that could kind of do this. No one made a link with live programming, and no one actually made a language like Cascade. So yeah, I don't know. Maybe I'm late, or maybe I'm early. I don't really know.
Okay, thanks.
Yep. Oh, but I'm in between you and your coffee, so maybe I should just let you all go.
Well, let's see. Do we have we do have enough time for one more question if someone does have a question. Yeah.
Thanks. Thanks, Remer. This is great work. I like how you used some. You said there was some connection to fixed point searches inside this data flow graph. I was wondering if you could elaborate on that a little bit more, and so as you're cascading certain changes through this graph, how do you visualize that? Can you give an example of how that search works?
Inside the paper, there is an example of what a transaction looks like that has more cascading changes. In terms of a fixed point computation, what I normally do when I express one is I schedule a check in the future that checks if anything has changed or not. And if it has changed, then it has to recompute the part of the computation that checks, that propagates the change, and then again schedules a check in the future if the changes are done and no more changes can be observed. And because we can schedule events in the future and they don't immediately happen, it means that we can do stuff in the meantime and then do the check in the future. So by its scheduling mechanism that has stuff before and stuff after, you can express those computations. And then basically you see a kind of, an unwound loop. And it's, you see a lot of side effects
do you have
happen.
Like, how do you implement this? Is it in a programming language that has support for continuations, or what language is this written in that allows you to do this efficiently?
It's written in Cascade and it runs on Delta. So actually, it has basically on top of C#, and at the lowest level it's edit operations. Everything goes to the history. And is it efficient? Well, that's a good question. I have no measurements on that, but it doesn't execute anything that it shouldn't execute. In other terms, if efficiency, currently it stores everything in the history. You could also say that's an enormous memory leak. On the other hand, you can delete the history at any moment that you like, but then of course you can no longer inspect it. And I'm interested in showing and inspecting the history. So there are still some questions there that I need to answer.
Cool. Thank you.
Thank you.
Hey, one more round of applause for Remer. Thank you.